Hello, welcome again. We are covering the subject fluid mechanics for various gate exams. Next topic in the chapter of properties of fluid is types of fluid. First, we will define ideal fluid. A ideal fluid is a fluid which is incompressible and has no viscosity. Okay, so that is your ideal fluid. So no fluid is ideal because it is an imaginary fluid because every fluid has some viscosity. So as viscosity is 0, so according to Newtonian law, shear stress will be 0. So this will be represented by, suppose if we take on vertical axis shear stress and here the velocity gradient. So as viscosity is 0, so the ideal fluid will be represented by this line. Okay, because shear stress is 0 for each and every velocity gradient. So this is your ideal fluid. And ideal solid will be represented by vertical line because there will be no velocity gradient and there will be shear stress developed in the ideal solid. Now first type of fluid which can be a real fluid is Newtonian fluid. So Newtonian fluid is the fluid which obeys Newtonian law, and Newtonian law is shear stress is directly proportional to velocity gradient and proportionality constant is your dynamic viscosity. And other classification of fluid or other types of fluids are non-Newtonian fluids in which there are various fluids. The general law for non-Newtonian fluid is shear stress is equal to mu du by dy raised power n. So if we take n is equal to 1, then it is Newtonian fluid. If we take n greater than 1, then it is diluent fluid. For this type of fluid, the shear stress will be work for the given rate. More shear stress will be work for the given rate of strain because here n is greater than 1 and this quantity will create more shear stress as compared to this, and this is due to the increase in viscosity as the shear stress or shear force increases. Okay. Because here if we take this as a law, then as this shear stress increases, this viscosity also increases. Okay. Next type of fluid is pseudoplastic fluid. For that n is less than 1, okay, and less shear stress developed for the given rate of strain as compared to Newtonian fluid that n is less than 1. This is due to decrease in viscosity or shear or viscosity as shear force or shear stress increases. Next type of fluid is Buckingham plastic. So here some constant shear stress is acting always. Even this du by dy is 0. After that it may start following Newton law. So this is the constant shear stress which will occur in the Buckingham plastic or which is required to generate the movement of the plastic. Okay. And after that this strain can take place or strain rate can take place. So this is the minimum value of shear stress required to begin the shear strain. Okay. So this is called Buckingham plastic. One more definition with this non-Newtonian fluid is your apparent viscosity. So apparent viscosity for any fluid, this the Newtonian law can be expressed as this apparent viscosity into du by dy is equal to shear stress, because this value is changing in case of diluent and pseudoplastic. So at any instant we can relate this. So this is at a particular instant we can relate this shear strain rate and shear stress by apparent viscosity. So shear stress is equal to apparent viscosity into du by dy. Okay. So du by dy again shear strain rate, tau is shear stress, and this is your apparent viscosity. So this value will be different at different strain rate. So this is at a particular strain rate, so that is called apparent viscosity. But if we take the constant value of this viscosity, then the law for any fluid is tau is equal to mu du by dy rate for n. Here this value is constant, but here this value is variable. So that is at a particular instant of time. Okay. So when n is 1, then it is Newtonian fluid. When n is greater than 1, it is island, and n is less than 1, it is pseudoplastic. So if we equate these two at that instant, then mu du by dy which for n will be equal to apparent viscosity into du by dy, or apparent viscosity will be equal to mu du by dy which for n minus 1. This is a constant value, but this is variable. Okay. If we take n less than 1, then this will be in du by dy, and power will be negative, or it will be in dy. So it means apparent viscosity will decrease with the shear strain rate. Okay. So when we take n greater than 1, this will be more than 1, and apparent viscosity will increase with this shear strain rate. Okay. So this is the apparent viscosity versus shear strain rate. When n is equal to 1, then shear strain rate and sorry apparent viscosity and dynamic viscosity will be same, or it will not vary with your shear strain rate. Apparent viscosity will not vary with your shear strain, then the graph will be like that.